So today's session is on monads. So today's session is on monads, primarily in Scala, because that is where, uh, as in terms of data engineering, we are most likely to use it. Is my voice audible? Can somebody confirm?
Yeah, Joy, I can hear you well.
Okay, thank you. Okay, so I'm betting on the fact that a lot of you already know what monads are in Scala or generally also. Also, maybe you've worked with parts of it. There will be parts of the talk will be repetition of what I have spoken in other talks, like the talks on composition, and then there was the talk on data expectation. Parts of it will be similar, but I'm just trying to focus on monads and put everything from the monadic point of view. Okay, how does all those concepts tie back to monads? Okay, so let's start. So this is one of the quotes, not quotes really. This is a paragraph which I found in a book on category theory by Barthos. If you go on YouTube, he is probably the only person who is teaching category theory for programmers, and you'll be able to relate to. So you can take you can check out his videos. There are other people also teaching, but I felt that this guy is the one who is really does it well and something which the programmers can understand. And it's a very succinct description of how we look at monad and we get perplexed by the concept. So what he's saying is, if you look up a duct tape and its applications, okay, there are multiple things that a duct tape can do. Okay, it can, he's given some usage, but looking at the applications, if we try to understand what is a duct tape, that is probably a very bad way of looking at it, right? You would never be able to harness the entire power of monads. Okay, so monads is like that. We generally look at one interpretation of it, okay, and we try to gauge what it does. Okay, for somebody who is looking at it from a say fixing Apple iPhone point of view, he will know that monad fixes Apple iPhones, right? So this I felt is a very good quote. So starting with this, so now let's see what a monad is really. What is a monad really? Okay, we have heard a lot of talk about it. Okay, so how I've read multiple blogs on multiple places, and many of those blogs only describe an aspect of it. Okay, like this guy has put it very succinctly in his post that many of them are just trying to tell us what this duct tape does, and nobody really covers the concept because a monad is such a data structure which has multiple applications. It's not also possible for them to cover all the use cases and tell you, okay, this particular thing does this, okay? Because there's a lot of applications. Like a duct tape has a lot of applications, right? So probably the best way to describe a duct tape is to just put it out there, that this is a duct tape, and then let people figure out what it can be used for. Okay, so that's why I put this quote here. So what I have felt uh, that we should explore when we are talking about monads are these three things. Okay, so one of them is the sequential computation. Monad brings in sequential computation, so we are going to explore this aspect of it. We are going to explore the aspect where the data structure or the structure of the monad itself, f of a, that particular structure itself will explore, and then we are going to explore the effects. I've already spoken about effects in one of my talks. So we are going to explore that aspect also only from the monadic point of view. There are many effects that you can find, but we'll focus only on the monads today. Okay, so keeping this diagram in mind, I will kind of take a piece of this cake one by one, and I'll try to explain that. Okay, let's move on. Okay, so let's get it out of the way first. Okay, what is a monad, technically put, in terms of code? Okay, so a monad is something which has a pure and a flat map. That's it, nothing more than that. Okay, so there's a pure. You see what is the structure of pure, or what is the type signature. It takes a returns a f of a. F, you can think of it as of now like a container. I haven't explained f as of now, but you can think of it as a container which holds a. It takes a and somehow wraps it into this container. Okay, what is flat map? It takes f of a and it takes a function which itself takes a and gives back a f of b, and finally the effect is it gives me back a f of b. This is it. This is, technically put, let's get this out of the way. This is the structure. Anywhere you find these two things, flat map and pure, it's a monad. That's it. And then all the properties and stuff that we will explain or discuss today will apply to it. So you can think of it, this is a visual cue, how you can identify what is a monad. Pure, flat map, it's a monad. It has to be a monad. Okay. And sometimes when you're going to use, you're going to think of something like a monad and start using it like a monad, it will actually give you an error that flat map is not a member of this class. You're trying to use a class which is not a monad, and you're trying to use it in a monadic way. So it will give you, the compiler will give you that error, Scala C or whichever compiler you're using. It will give you the error that flat map is not a member of this class, or pure is not a member of this class, based on which function you're using. Which this error, as soon as you see this error, you should understand that this class is not a monad. Okay, otherwise you could have used it like a monad. Okay, and generally this is not important. That's why I've colored it as green. Most important are the first 2 points. Generally, it also has a map. Okay, a map has this signature. We all have worked with map at certain point in time. It is a transformation function. You can think of it. It takes a, transforms the a to a b. Okay, so this is the map function, and therefore it is also a functor because functor has a map. But we'll not get into that today. This is for another day. For we'll get into why it is a functor and how it helps. We'll get there. But it also generally has a map. You generally find this type signature. It also has a filter, but again, we'll not get into that today. Okay, so the main parts that we're going to focus today is pure and flat map. That's it. That's all that you have to understand, and that's the takeaway of the talk. How to use flat map, that's the main takeaway. Okay, moving on. So you remember from a previous talk, just one second. From a previous talk, we had explained this concept of reification. Okay, it is contextual here, so I have just taken the same slides from that. I think data expectation, same slides I've taken. So there is a concept of reification in Scala. I was talking about this. What is reification? So first thing is, if I have to talk about reification, first thing is something which was abstract, make it concrete. Okay, something which was implicit in your code, make it concrete now. Okay, so what does it mean? Take some concept that was implicit in the code, turn it into data, which can then be manipulated by the program. Okay, this if you see this behavior somewhere, okay, it can happen in multiple places in Scala. Most of the data structures, most of the data, what things which you perceive as data are actually some kind of implicit code, and they're reifying it to give some meaning. Okay, so basically some concept which was implicit into the code, turn it into data, and then let the program manipulate it. Best expressed, all these things best expressed with an example. Okay, let's see. The first example, I had explained this earlier also, functional programming itself. Okay, so in hooks, functions are not data. If you remember, functions are not data. Why? Because you cannot pass around functions like data. We couldn't pass around functions in Java, right? You cannot pass a function, maybe with the later versions of Java, but in pure hooks, you cannot pass around functions like data. Okay, but in functional programming, it is possible, right? So what they're doing is they're reifying the concept of functions. At the very beginning, functions are made the first class citizen, and they're reifying the concept of functions here. Okay, so that's the first point. Functional programming itself reifies a lot of concepts. Then there is option, which reifies the concept of partiality. We will come to this later. I just want to get this done with. I actually copied these slides. So there are more examples. Okay, it is everywhere. we are talking about some reification of the concept of effectful composition. Okay, that is called Kleisli. Akka streams, if you've worked with Akka streams, you'll know there is a concept called flow, which is the reification of the concept of processing stages. Okay, so the data is the streaming data that comes separately, but they have reified the concept of processing stages. There are multiple processing stages and different kinds of flows. Okay, earlier it would have been implicit in the code. You get the data, you do something with it. Now they took that concept, made it first class constructs, made some case classes or something. So that means they are, although these are case classes, they may look like data, but they're actually some concept which they have taken and made a first class citizen in the language. So the language of Akka streams is in terms of flow, which is reifying the concept of processing stages. Okay. Most recently, we have reified the concept of DSL. In data expectation, we have reified the concept of data expectation into a DSL using free. That itself there is a reification. Okay. Same goes for trampoline. So the stack safety, earlier we would have some implicit code which would handle stack safety. Stack doesn't blow up, right? Trampoline is, if you look into the CATS library, I think, yeah, CATS or Scala Z, if you look into the library, you'll find trampoline is a first class construct which you can play around with, but that construct is specifically defined for stack safety and how to manipulate that. So it makes these constructs available. Option in particular, if you think about it, it gives you a construct which talks about sum or none, which is partiality. You always, so in Java, what we used to do, if you remember, if you don't have something to return, we just don't know what to return. We returned a null. Okay. And that caused multiple different problems, right? Null pointer exceptions being the most famous, different kinds of issues in our code. Okay. So that concept has been handled. So there was something implicit in the code. The null which you returned embodied the concept of partiality, but it was not spilled out anywhere. It was not stated anywhere that this null means partiality. I don't know what to return, so I returned a null. Now, taking that concept, we are reifying it into option. You get a none. So you know your code cannot, so your code, the code has, when you write functional programs, it would automatically not do anything if you have a none. Okay. And you don't need to make special handling cases for it. Like if this not equal to null, you would do something, right? Then only you start writing your code. Every function, say suppose you have two functions, they are called within each other, or three functions, two of them are called within each other. Everywhere you would do a null handling and then only proceed. Now this is taken care out of the box. Option gives you a none. When you combine these three pieces of code, if there is none, the final answer would be none. And if there is only if there is a sum, the entire computation would proceed and execute. That's the idea. Okay, so that is also a reification of the concept of partiality or null, whatever. Okay, so keeping this in mind, okay, we'll move forward with the concept of monad. Okay, so what is monad doing now? Why did we speak about reification? Because monad is reifying the concept of sequential computation. The concept of sequential computation is being reified. We all know we perform computations in sequence, one by one. First this, then this, then this. Okay, but monad is reifying that concept. How? So first, let's look at this structure. Okay, this f of a, what we generally have whenever we talk about a monad. You generally focus on f of a. Okay, what is this f? This f is a program. Okay, and a is the value produced by the program. Very simple. You run the program and you produce an a. Okay, and then there is also a naive thing that a lot of people say that a is this f is this extra mechanism which has everything else. It contains everything else which is not a. I mean, that is quite observable. That is quite apparent, right? But yet that has a very important meaning. F is everything which is not a. F is that entire supporting mechanism which is not a. So it can be looked at from multiple points of view. One is You run this program and you get a, okay, the value that is produced by the program. But also, can you think of other things? Okay, when you say option of a, option of int, it encapsulates that extra machinery or that extra concept of partiality. It kind of keeps within itself the extra mechanism which computes or does whatever needs to be done when a null occurs. So that is that extra machinery I'm talking about. Okay, that is f of a. Okay, so it's a program and a is the value that is produced. Okay, let's take a moment here because this is important. Okay, if you really think about it, uh, f of a is really the crux of how it can be thought of as a container. Most of these data structures that we see in Scala are really containers of some value. Okay, containers of some value. But then that container itself has some logic embedded in it. How cool would it be if I can embed all these logic in different containers? Okay, a logic of exception handling, a logic of dependency injection, and then use these containers as if though they were standard containers and keep, composing them and start playing around with them. So if you see, the a here is pure and the container is taking the pain of encapsulating all the extra machinery. Okay, so having said that, okay, having keeping in mind what is f of a container of a, let's look at flat map. I think this itself will spend some time on this slide. We're in no hurry. If you have any questions, let me know. And a lot of you already know about this. If I'm not able to explain in the best of manner, feel free to jump in and try to explain, because we all want to take this concept back when we leave this session today. Okay, and then figure out how to use it in our programs that we write. Okay, how to write purely functional programs. Okay, or at least programs which uses monads, because monads provide a lot of advantages. Okay, so let's spend some time here. What does this flat map take? Okay, um, my first introduction to flat map was with list, and I used to think that, okay, it took some element. Okay, it used to take a function which would take a and return me a list of b, probably. Okay, so I always thought, initially at least, I always thought it had an effect of flattening. Okay, it's flattening some element to multiple elements. Okay, but that's not what it is really. Okay, if you look at this um, first line of code, okay, you will see this code embodies the essence of sequential computation. This is what a sequential computation is. How? Let's look at that. You get a f of a from somewhere. You get one program from somewhere. Okay, and you somehow strew it around. Okay, you pick out the a from this f of a. The first, okay, 1 second. Okay, you take this f of a, you get this f of a from somewhere. Okay, and you pull out the a from it, you pass it into this f, and you get a f of b. Don't you think this is the reification of the concept of sequential what does a sequential computation do? It sequences things together. It's like a pipeline. If you've used those Unix sed grep, right? You first do something, and then you do grep, and then you pipe it, and the output of grep is the input to some word count, and you do a word count and you print that. Then you pipe that and you print that, right? If you see, this is really a pipeline, and this is the essence of a sequential computation. This is one intermediate stage. You can think of one intermediate stage in a sequential computation. Okay. And the best part is these monadic programs, or however, the structure is dynamic. We don't need to know what F is. We don't need to know what B is. This type signature just works. I don't need to know what is A. Right now, I've just defined it on generic types. I don't need to know what is A. I don't need to know what is B. I don't even need to know what is F. But I'm able to sequence all of them together just by the fact that, there is some program. Now, what I said was about this is there is some program, okay, which produces an A, right? So there's some program which produces an A. You took that, you pulled out the A from it, and you passed it into this next function, which took an A and returned you a f of B, which itself can be a program. So a better representation can be this. Okay, whatever I've been trying to explain can be explained like this. Okay. So the second, if you see here, the second program depends on runtime value produced by the first program. We don't know. While writing code, we don't know. The second program. So if you see, this is the, I already said that this is a program. Think of it this as a program producing A. Okay. And think again, this is also a program producing D. So if you see, the second program to run depends on a runtime value produced by the first program, right? Only when this guy produces A will you be able to run this guy, right? But this is really the crux of a sequential computation. If you think about it, there is a first program. What is a sequential computation? Joining two programs, right? And kind of creating a flow out of it. Okay, one by one, you execute code, right? So this is the basic of a sequential computation, right? You take a first program and you take a second program, you join them and you make a result program. A lateral observation here is, it is also a composition from my compositionality talk. If you think about it, I'm composing two things together. I don't know what the runtime value will be. Second program depends on first program. Okay, and the first program also needs a runtime value. Okay, but I don't know. Everything will be evaluated at runtime. But I'm writing constructs and I'm writing program as if though they were already there. Okay, and finally, what you get out of this is the result program, which is f of B. And now, if you see, you can take this entire program and use it as one program, right? So this really translates it back to the fact that you can compose two pure functions, and the result is a higher order function, which you can start using anywhere, as if though both those functions, the two functions which you composed got absolutely abstracted out, and the higher order function is now encapsulating the functionality of both the functions. Okay, so this is really the crux of what a monad has. First, the first take-home point is sequential computation. It is reifying the concept of sequential computation. How is this? In this way, you take one program, you take f of A, pull out A, screw it to F, and you get a f of B. Okay, so just giving a moment there. And if you see, this is all dynamic. Like I said, I don't know what f is, what A or B is, but still I can do sequencing using them. I don't have no idea what the types are. Int, string, I don't know. But or f is an option or some other monad, I don't know. But I can do sequencing using them. Okay. Okay. Having said this, let's see how I can do sequencing. Okay. Okay. I think first we'll look at this structure. Okay, how we can do sequencing. You can do it on your own as well, but there is a novel expression that is already provided. A lot of you might have already used it. Just reiterating here, that is the for expression. Okay, the general structure of the for expression. If you see here, I've tried to put. I've not written any code here. I've tried to put the general structure of the for expression. Okay, you have some code, okay, producing f of B. You pull out the B, then you have some code f of C. Okay, and how it pans out is like this. Okay, so now I've tried to concretize a bit here. So you have a function 1, which takes A and returns you an option of B. I'm trying to use some concrete types because talking about a lot of F's doesn't make sense. So what is this F? This is the program, right? Option, we may not have thought of option as a program, but we will very soon. If you think of option as a program which encapsulates the concept of partiality, So I'm saying it provides me with partially an object of B, may or may not be there. B may or may not be there. But if it's there, it will be encapsulated in some. If it's not there, it will be none. Okay. So this program, which is encapsulating the partial behavior of B, is the function 1. Then there is function 2. Then there is this is a mistake. This should be function 3. So, and how this for expression translates, when you write a for expression internally, what happens is basically this. Okay. So just take a moment here. From this flat map, we've started from this flat map. Okay, f of a, and there was a function which took a and returned f of b. We took this and we started writing some code based on it. Okay. So what I'm saying is, if you really see, this is nothing but sequencing these pieces. I took a function which took an input a from somewhere. This input was taken. This function takes an input a. This returned an option of b, out of which b was pulled out and passed into the next function, which definitely takes a b. So there is a type matching that is also happening. Automatically, these would not compose. So when you write at compile time, you cannot compose f1 and f2. Okay, function 3. This should be function 3. It's my bad. Function 1 and function 3 won't compose because this takes a C and this returns an option of B. If you try to call a flat map and you try to compose them, they won't compose. You have to put this function 2 in between because this takes a B and this guy returns an option of B. Okay. And this is how the code would be strewn around. You take a function, you take function 1 takes a you call flat map on top of it. There's a B, which you get. This B is basically the B pulled out from option, and that B is passed into function 2. Again, the same thing. You take this flat map, you call a flat map on top of it. But how are you able to, now question is, how are you able to call this flat map? Function 1 didn't have any flat map. How are you able to call it? You're able to call it because option has flat map. So function 1 of A, when you call, you get an option of B, right? Think about it. When you call function 1 of A, you get an option of B. And on top of that, you're calling flat map. And that's how automatically returning a monadic type helps your program to strew things around, helps your program to sequence computations. Okay. So you call a flat map on top of this option where you're able to pass the B. When you call the flat map, the signature of flat map enables this. The signature of flat map pulls, this code is encapsulated here inside flat map, whichever monad you're using, option or something else. Okay. It's encapsulated here. This guy does the work of pulling out the A and passing it into F. Okay. You just have to provide the F. And that is what I'm doing exactly here. I'm providing what is the F that should be passed, which is function 2. And that is passed here. And then B is passed inside it. Again, B returns an option of C on which you can call a flat map. That flat map does the work of pulling out the C from option C and passing it into the final function 3. So I've not written this here. This is function 3. Okay. Passing it into the final function 3. It's causing me also a bit. Okay. Okay. This is what a for expression boils down to in terms of the monadic context. Okay. There are other things also. You can do a filter. For expression also supports map operations. Okay. But that's a separate talk. Probably we'll cover it on the functor when we are explaining. But today, if you really think about just monads, this is all that is called. Okay. This is all that is called. So this for expression. Now, one thing that is important that you can see here, I've already written, F should remain constant. Okay. You cannot change the F here. It has to be, all of them have to be option, or all of them have to be, say, reader or writer. Okay. All of them have to be that, or either. Okay. F should remain constant. Having said that, then for expression can easily, the compiler can inspect your code and figure this out. Okay. So it is interpreted, although it is interpreted at runtime, you can write code in a way, in a type safe way, where you can sequence computations without even knowing what their signatures are, right? So having said that, we'll do a demo. We'll check here if whatever we've said holds or not. Okay. So let me stop presenting 1 second. And let me present my entire screen. Just a small demo. You'll probably find this in other courses or somewhere as well. But just to prove the get the point home. Okay, so there is this function one. My screen is visible, guys? Think so?
Yeah.
Visible, right?
Yeah, thanks. So you have this function one, function two, function three. Very simple. It takes a int, does nothing, encapsulates in sum, and just returns the same int. Second guy converts into a string. Third guy converts it into a double. Okay. So if you see this, I have run this here. I can run it again. If you see this, when it is interpreted, what I'm trying to show here is this is the for sequencing. Okay. For function one, I passed in the for sequencing, I passed a. Okay, and I took this guy took this a, took the b, pass this b inside this. Okay, then this got a c, pass the c inside this, got a d, and that is the d that we are yielding. If you see the output type here, automatically compiler is doing this for you, or rather IntelliJ is doing this for you. It is inferred to an option of double. It will always be encapsulated in your monad. This is automatically done out of the box for you. And I have resolved this into the code which I had shown on the slide. These two are producing the exact same results. Okay. If you see, I've just called them one by one for and result sequencing. It's exactly the same. This is what for expression is doing internally. So if you write this code, it's not wrong, but aesthetics wise, we would try to use a for because it kind of tells you what the program does. Okay, these functions might be some relevant names, some contextual names. Okay, and you will know, okay, first it does this, then it does this, then it does this, and this itself becomes a kind of documentation. Okay, and would again, not only documentation, it's also important from the point of view of modularity or composition, because all of these this can itself be a module on its own. Okay, this is module one, this is module two, and this is module three, and you're composing all these three modules to get the final answer. It can be looked at it that way. There are other I've already had one session, we'll have another session on why things should be pure, how easy it is to test, how easy it is to keep things modular, to assert, to do equational reasoning. All these points I've covered, and we'll do it in a later session as well. But the idea is, whatever, let's say if pure functions, if we accept for today that pure functions is the way to go, and functional programming is something that should be preferred, then this is for expression is a very important weapon in your toolbox. You have to use for expressions. Think of it this way. You can do it yourself. Okay, you can write all this code, but this will just complicate, and the reader will really be struggling to figure out, okay, iske saath flat map kiya, then B got passed in the other, right? So you really have to harness the power of for expressions, because it's not only about getting complicated, it's also about harnessing the power of monads. And by monads, I mean harnessing the power of sequencing computations. Okay, you can put in different kinds of computations. You can sequence them. You can have a fork, a join, right? Here, if B has this value, then call this function, then or else call a func4, which does something else. And you can really write great sequencing computations, sequencing programs. Okay, and that is the essence that we're trying to show here. Okay, these two, but this demo is really about structurally these two are equivalent, and when you call them, they produce the exact same answer. Okay, which is an option of double. Okay. All right. Any questions till now, guys?
One question, Joy.
Yes.
Apologies from before if I'm not using the right terminology, but
No problem.
when you show this example, right? So the associativity you're showing, right?
Yes.
The way you're able to pipe the operations, if I call it that.
Yes.
Now,
Yes.
so given a monad, like what is the difference between this and what like the typical associativity of functions that we think of in functional programming? Are they different or are they always the
They
same?
are not different actually. They are same. There is a trick that we play in monads. I would say if we think of them also, so let me put it this way. If we think of these also as pure functions, okay, how can we, the idea is when we talk about associativity, we can compose pure functions and get some answer. Okay. Now the real problem, okay, the real problem with uh, monads or functions which produces monads is the problem that it encapsulates some effect, okay, and we should have a way of associating or composing monadic functions or effectful functions, okay, and that is something which is done using one another monad, which is a Kleisli. Okay, we have a talk for that as well. What you're saying, we have a full talk for that. How you can think of pure functions at one side and how you can go ahead and think of these monadic functions as a pure construct and how you can compose them. I think I have done one previously on intuition or compositionality, and we will again have that talk, how you can associate them together and produce one answer. But conceptually, if you ask me to answer your question, it is basically we have to think of this also as a pure function or a pure operation. I would rather call it a pure effectful function, okay, which produces an effect of partiality along with the value, and how I can now compose these things together. So if I have time today, I'll cover that part also, how you can compose them together. Does that answer your question, Sudarshan?
Yeah, and one other question is like, I mean, again, so I understand like the example that you gave regarding FX, like for example, null handling is one. Now, like if I don't talk about monads, in general, associativity does it generally include taking care of the effects within the next program or function itself, whereas in a monad, it is something externalized. Like, what is that how it is?
So there are multiple ways of looking at it. One way of looking at it can be you can handle it within the function. Okay. So if you say, suppose your function is the one which produces some kind of exception. Okay. Now, one way of looking at it is you can either, instead of throwing an exception, you can encapsulate it within an either. The right of the either will contain the answer and the left of the either will contain an exception. However, this entire way of handling effects, how you want to handle effects, can also be delegated to a totally different data structure. There is a free monad or a free data structure which can be used to encapsulate this entire way of handling monads. So if I understand your question correctly, what you're saying is, can there be a way of segregating these two concerns? One concern is to compute the pure value, and the other concern is to do the side effects,
Right.
right? So there is basically one machinery which is going on handling all the side effects, maybe like an aspect oriented programming way, handling the side effects, handling logging, handling all those
Right.
things.
All the
There
cross
is
connect.
another part
Yeah.
which is doing the computation of the pure value. Yes, that can be done. It is a choice of the programmer really. So the more and more we dig into it, I have already, there is another session pending, or there is already a talk given on free monads where you can segregate these two concerns. One machinery can work on just doing generic logging, dependency injection and all those things, and another module is probably useful or used to compute the pure value. So maybe what we can do is we can build the generic library or the generic modules which does all the classic work, log handling, error handling, things like that, and then people can only be concerned about writing what the pure part of it does, because that is really the business logic. Everything else is handled out of the box, something like that. Does that make sense?
Yeah.
Okay, great. Cool. So, okay, then we'll continue. 1 second, guys. I'll just share my screen again. The tab basically. Okay. So yeah, I wouldn't call it a demo, but yeah, I had to write something. So it was just to assert that these two are exactly the same thing. Okay. Um, okay. Next thing that we are going to explore is basically what Sudarshan was talking about, the effects part of it. Okay. And what are the different kinds of effects and what is an effect, things like that. Okay. So if you really, okay, I'll not go to this slide first. Let me go back here. If you really look at this, okay, this f of a, it is f here. This f is an effect. Okay, so let me second. Now let me say that let me bring in this new terminology that this f is an effect. Okay. This f encapsulates some kind of effect. It can be the effect of partiality. It can be the effect of exception handling, the effect of a dependency injection. But this F is the one which is encapsulating the effect. Okay. Earlier, I was just giving a vague term, program. Okay. But now I am concretizing what this F means. It is a program which produces an A with the effect of partiality. That means you will have an option of A. It is a program which produces A with the effect of exception handling. That means you will have an either of A. Okay. So this is what the effect really boils down to. So the problem with monadic computation is you cannot really write pure functions. Okay. So what even Sudarshan was pointing out, you cannot write. So what is a pure function? A pure function is something which takes an A, gives a B, A to B. Okay, that's what really is a pure function. Okay, this guy here is not a pure function. Okay, if you look at it, there, 1 second, guys. If you look at it, this guy is not a pure function. This guy takes an A, returns me an option of B. A pure function would take a, give me a B. That means the output depends on only the input and the algorithm contained inside this pure function. Okay, but I'm still saying, I'm still positive, or I'm still kind of trying to prove that these are also pure constructs. And we will go to that. That is our next session. That is our next continuation session on how we can compose. Okay, so I have actually already told you how we can compose. If you really see here, okay, but there is a reification of this concept as well. Okay, if you see how we can compose, so pure function composing is very easy. Okay, A to B, B to C. You can just call one with the other, right? It can just be, so function one, it's like an equation that you can write. Function one, and within that you can call, say, rather function two. So let me just write it down to concretize. I think you guys are already understanding, but just to concretize. So if these were pure functions, is what I'm trying to say. Okay, so you would just write it this way, right? That's it. That's your composition right there, right? Composition right there. But this is not possible directly. If you see this thing, this guy is not possible directly in these cases. And the problem is these effects, this F, which is associated. So somehow I got to pull out the B from the F to and pass them in this function 2 to achieve the effect, to achieve the final answer, which is C. And that's exactly what flat map is providing. And then this item is reified again. The reification concept is coming. This again is reified into a concept called Kleisli, which does this for you. Don't have to do it. You can either do it in a for, but you can also do it using a Kleisli. We'll get into that later. But the idea is really this. Okay, how can pure function easy to compose? A to B, B to C. You can compose. You can say, you can give a one function which returns A to C. Okay, considering these were pure functions. This is not pure. Okay, I'm not saying this is not pure. I'm saying this is a pure effectful function. I'm saying this is effectful, and I'm kind of saying that this effect is also pure. This effect doesn't do any kind of impure or side effects. Okay, and then what I'm trying to assert is I can compose them, albeit I have to use a special construct. Okay, so if you're aware, we have some construct called and then, right? In our this thing in our Scala. So that and then is not applicable in a effectful function. Okay, so now we have to use this construct of flat map. Okay, so yeah. So now what is the, so having said all of these things about effects, okay, and I'm also drawing the fact that you have been in my other talk, which is on compositionality, that you already know I had explained these things, that what is the problem here. So what is the bare minimum effects that you got to see? So there was a paper by Eugenio Moggi who said that if we have these effects that can be encapsulated in a monad, okay, this is pretty much good enough to start your own toolbox. You can handle most of your code, most of your side effects using these concepts, using these, because these encapsulate the basic set of side effects. If you see the concept of partiality, which is computations that may not terminate, okay, non-determinism, computations that may produce many results. Your function doesn't produce one B, it produces many B's. Okay, how would you do that? Then there is side effects, albeit the most classic ones are computations that access or modify state. One is a read-only state, which is an environment. You read an environment, right? You think of dependency injection here, probably. You read an environment and you work with that environment to produce some value. A write-only state. Along with your work, you're doing some kind of logging, if you think of it. And then there is a read-write state, okay, where you do both update and you read. Okay, that kind of problem. Next is you have exceptions. Okay, what are exceptions? Partial functions that might fail. It will always produce the answer except that one time when it hits a snag. Then there is the concept of continuation, ability to save state of the program and then restore it on demand. This is exactly the concept of Kleisli. Okay, and then there is interactive input and output, which IO, standard IO, which we take. Okay, these are the problems that we intend to solve. Okay, and these are the most common problems in your toolbox that you'll be facing, and that makes your program side effectful. Side effects obviously are everywhere, but these are the main effects which make them side effectful. If we can look at handling all of them in a pure setting, then we can write pure code. We can write pure functions always. Okay, albeit there will be some change to the structure, like I shown, which was instead of using them directly, we have to call a flat map on top of them. But there are constructs to do them for you out of the box. Okay. So having said this is the problem, the solution is this. Okay. Some of them are already provided in the Scala library, or rather the Scala language. Some of them are not there, but there are other libraries where you can find it. There are many libraries which you can find in anywhere, like I think in JavaScript or everywhere you'll find these libraries which gives a reader, a writer, a state. In our case, we use GATS, but a lot of people use Scala Z. You can find it there as well. So now to explain, the solution to all these problems, or the effects which these monads are producing, is this. Partiality is encapsulated by option. Non-determinism is by list. Side effects, the read-only state is encapsulated by reader, which is classically used for dependency injection. Write-only state is used by writer. Read-write state is used by the state monad. Exceptions is by either. Continuations is by Kleisli, and interactive input-output by IO. So if you know how these work, okay, at a high level, you will be able to do functional programming, at least in the monadic context. Okay, so you will be able to handle all your code in a pure setting, and then execute them. Maybe obviously there will be a driver where you will be doing some kind of side effects, but that will not affect your internal code, which are your modules. You can write pure modules, have them unit tested, have them do what they say they do, and not do some logging or some exception handling on talking to some DB. Okay, they will do what they say they do, and then you can wire them together to get the final result. Okay, so these are the ones which we will be exploring over the next couple of weeks, these monads, and how to use them, where to use them probably. Okay, so the most easy ones, I think we don't have much time now. The most easy ones I'll show, and maybe we'll not cover all of them today, but if you just look at the structure of how these things look like, it will make much more sense. Okay, and all of these talks, little bit they draw from the previous talks. So first, let us look at option. Okay, so again, this monad that you can see here is a type class. So this is from the cats library or the Scala Z library. This is a type class. And if you see here, the concept of reification is coming in. What did I say in the concept of reification? Something which was abstract, make it concrete. What was abstract? The abstract or the implicit part was when you return null, the implicit thing that you were trying to say is this program sometimes produces result and sometimes doesn't produce result. Now we are taking that, converting into data. By data, what do you mean? Case classes. So you have a case object none, and you have a case class sum, which encapsulates your value. Okay, the implicit concept of partiality is now converted into is now reified, rather the correct term to use is now reified into data. And now you're using the concept, okay, of partiality in your code. You're playing around with these options, right? You're passing these options, working with them and things like that. Okay, you're playing around with them to do your further coding, right? But what we have done here is reify the concept of partiality itself. And then to make it more usable, we are converting it into a monad. How? As we said, we just need to focus on two things, pure and flat map. If you see the pure here, so I'm not going into the signature here. This is the signature of a type class. And the pure here takes a, returns you a sum of a, right? And the flat map here, if you see, just focus on the flat map a little bit. It takes a f of a, which is a f, if you remember from the previous slides. It takes an option of a, and it takes a function which converts a to an option of b, which is exactly the demo which we saw, right? There was another function 2, which took an a and converted it into a b. And this is the extra machinery I'm talking about. This guy is taking care so that guy, so think about it this way, the f itself, where it is passing, might throw an error, or this option of a, which it has received, the f of a, the fa, I should be using the pointer device stuff. So this guy, this f of a, can give a none, right? Oh, I've moved to the next one. Now, this f of a can give a none, right? If it gives a none, so think of it this way, you didn't have to do the handling of partiality. This guy does the handling of partiality for you. Otherwise, you would have to send back a null from your code, handle it in your func1, right? But you didn't have to do that here. If this guy got a none, this would return a none, and the entire computation would fall through with the answer as none. Only if this guy got an answer, okay, this you got a sum of a, that a will be taken and that a will be passed here with the f. Okay. Take a moment to see how the sequential computation part works here. That's all that is the takeaway of this talk. How this reification of concept of sequencing computation is happening in a monad. The extra machinery of doing partiality is encapsulated by option. So you got a none, entire execution fell through. All you got was a none. It did not call this particular f of a. Only when you got an answer, f of a was called. And then all the func, they all returned an option. And the partiality is now handled by option. Earlier in your function, you would have returned a null and you were handling the partiality. That is pulled out. That is in a way reified or pulled out into another data structure or concept, which is handling your extra machinery. So what probably what Sudarshan was talking about, can we have other constructs which can handle this extra machinery? Option does it at a very minute level for us, and we would like to build such and more such constructs which would do bigger handling for us. But right now this is just another example where you are just writing a code which is producing pure values A to B, transforming an A to B, and the work of handling partiality is done here. Okay, let's go to another example. A easy example you've seen everywhere. Okay, either has a left and a right. By convention, the left should always have the exceptions and the right should have the answer. If you see, we are producing an either. The expectation result in data expectation framework is an either. It will either have a result or it will have an exception. Okay, but think of it here, the reification of the concept of exception handling is happening. We have taken the concept of exception handling, pulled it out of your code, and here we are saying this guy will handle it for you. Okay, now it is available as data, left and right, and you can manipulate this left and right somehow. So what this guy is doing now, again, the same structure, if we see what this guy is doing here, is it is taking this either, it is checking if it has a right, then from that right it is pulling out the A, passing it to f of A. What is f of A? Takes a, gives another either of L and B, right? So right here we have the essence of sequential computation, joining two things together. Okay, and if it had a left, it would just return that left. It would terminate. It would not collect all the errors. It would just terminate, because you don't have an answer to process. All you have is an exception. So it would just terminate from here, return the same left, and the entire chain of computation or the sequence of computations would fall through by returning this left. Otherwise, it would move ahead with this right, pulling out the A from the right and passing it into the next function, F. Okay, and finally, the last thing that I would like to show, this is the list. List is not really a collection in Scala or in functional programming, rather. Let's not talk about Scala. Scala, it is indeed a collection, but it encapsulates the concept of non-determinism. Okay, this is how a list looks like. If you see, either you can have a lot of results, that means a lot of B's, right? Then you would really have a list of B, which means it will either have nil, nothing, or it will have a lot of those values. That's all a list is, right? It has a nil, it has a head, and it has a tail, which is again a list. So it's an inductive data structure, right? So it takes a nil, it has a nil, or it will have a list which has a head and a tail. That's all a list is, right? So ideally, the way we should look at list or to process list recursively is to work with head and tail mostly. Okay, we generally try to iterate through a list and do computations on top of it. But the real, if you want to harness a lot of these recursive structures that is built out of the box, you'd probably look at working with only head and tail. That would give you a more power basically. And if you see again, look at this. This is the same structure over and over. I'm just showing these examples to get that thing, in our heads, that this is how it is. Okay, so look at this. Pure. What does a list have? List always has a nil at the end, right? So what it is doing is it is returning a construct which has a nil at the end. Look at the flat map. It takes a list, okay, pulls out every element out of it, and runs the function with that, and then appends the rest of it. That's it. That's all there is in a list. Okay. This is not only the implementation of lists pure and flat map, and how you can use list in a for comprehension. Okay. But this is also the monadic implementation. And this monad here is again implemented like a type class. where you can make anything a type class. Okay, how? Just replace your class list with your class. You have a class, and you are saying somehow I will make this class perform sequential computation. This has a meaning. Okay, it really needs to have a meaning also. But if you can do that, you can just implement this monad interface, and you can give what it means to be pure and what it means to be flat map. And then your entire thing will be strewn together. Okay, so just these three examples I'll leave you with. Anyways, we don't have time. We'll continue on the next day. Probably I'll tackle it from the pure and effectful computation point of view again. Okay, and then it will a lot of pieces, if today you have not understood, that will make sense then. Okay, but I am assuming that till now things till now it made sense. Any questions, guys?
Joy, one question is try a monad.
Yes, try is a monad. It has a flat map. My counter question. It has a flat map. If it has, it is a monad. I think it is a monad. My
I think,
intuition.
okay, I remember reading somewhere that try is actually not a monad. So
My simple
in
in the try data structure, right?
yeah, the try data structure, yes. The Scala try data structure.
Okay, 1 second. Let me just check that out. Try has a flat map, right? Yes, try has a flat
It
map.
does, yes.
Yes, so it is a monad. Means, see, the idea is, what is a monad? It is really a way to sequence computations. Okay, now if you consider something having a flat map a monad, then it's a monad. Okay, so technically it's definitely a monad because it has a flat map. But then, and it also is encapsulating the effect of success and failure, right?
Mhm.
So if you think that way, it is a monad. Okay, but I'm not sure why they're
I
saying
think
it's not.
this, so in true mathematical sense, there are few other laws that monads have to
Right.
satisfy.
So we have not
So
spoken, actually, we have not spoken about those
yeah.
laws today. So probably
Hmm.
next session or some other session, we'll speak about those laws and what you should check. Okay, yeah, that's a good, actually a very good point to add. So from category theory, I have actually shown those laws in another compositionality talk, that what are those laws. Either it has to have an identity, it has to exhibit associativity and all those things. Okay, so probably we'll tackle it that way. Then we'll so idea is, in mathematics we don't believe in what the person is saying, we believe in the laws, and we believe in proving the laws. So next day, if we are able to prove the law, then we'll say, okay, try is a monad. If you're not able to prove the law, then it's not a monad. So probably, yeah, we'll talk about the laws the next day from monadic point of view. Does that make sense? Okay, guys, any other questions? So I hope I was able to convey, um, but we'll sit again and we'll try to again brainstorm. Any questions, any things you guys have, just feel free to ping me and we'll have a discussion around it. Okay, and we'll pick up from here the next day when we start. Okay. Okay, I'll stop the recording.